We are in Chapter 5, Discrete Probability Distributions. The word discrete means countable number of values. And 5.1 is a probability distribution. Random variable is a variable typically represented by an x that has a single numerical value determined by chance for each outcome of a procedure. So example says, suppose you flip a fair coin twice. The outcomes are heads, 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 tails, tails, heads, or tails, tails. If the random variable x represents the number of heads in 2 flips of a coin, then the possible values of x are, so you can either have 0 heads, you have 1 heads, or you can have 2. Uppercase X is used to identify the random variable, and lowercase x is used to list all the possible values of that random variable that we have. So then we have a discrete and a continuous random variable, and we saw the word discrete and continuous back in Chapter 1. So discrete has either a finite or countable number of values. The values for discrete random variables can be plotted on a number line with spaces between each point. Continuous random variable has an infinite many values. The values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So next example says, determine whether the random variable is discrete or continuous. So the first one that we have is the weight of a steak. And weight, again, is a measurement, and this is something continuous. And so what we said before back in Chapter 1 was that continuous meant that like a weight or a measurement of some type, you don't exactly weigh 12 pounds. It might be 12 points and then a continuous decimal. So the next one that we have is the number of light bulbs that burn out in the next week in a room with 20 bulbs. You can count those. So that is an example of a discrete random variable. The next one that we have is the amount of rain in Seattle in April. Since we're talking about the amount of rain, that is going to be continuous. And then time required to download a file from the internet. Again, time is something measurable, so this is also continuous. A probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. So there are some requirements for a probability distribution. So the first one that we have is that there is a numerical, not categorical, random variable x. And this takes on numerical values that are associated with the corresponding probabilities. The second one is going to be that the sum of all the probabilities in your probability distribution will equal 1, and that those probabilities is going to be between 0 and 1, so they can equal 0 and it can equal 1 for every individual value of the random variable x. So the next example says to determine whether the distribution is discrete. Probability distribution, if not, state why. So the first thing that you have to check is that you have x is a numerical random variable, and for this problem x is numerical. We have 100, 200, 300, and so on. So x is numerical. It's a numerical random variable. The next thing that it says to check is that the sum of all the probabilities, so if we were to add up all of these numbers, that has to equal 1. So take a second and try to see if that equals 1. And when you add these up, you get 1.25, which is not equal to 1. So therefore, I'll put some 3 dots, which stands for therefore. This is not a discrete probability distribution. So once one of those 3 things is not met, we can say that it's not a discrete probability distribution. So part B, same question, different distribution this time. So first thing, your x random variable has to be numerical, and it is. So x is a numerical random variable. So I'll put RV for random variable. And again, second thing is checking to make sure the sum of all these probabilities equals 1. So take a second to add those up, and this time it does equal 1, so that's good. The third thing that we have is that your probabilities that we have that I boxed are going to be between 0 and 1. And all of those probabilities are between 0 and 1. So therefore, this is a discrete probability distribution. Next thing we have is if you do have a discrete probability distribution, we can use that to make a probability histogram. The horizontal axis equals the value of the random variable, and the vertical axis represents the probability of each value of the random variable. An example on the next page says hiring managers were asked to identify the biggest mistake that job applicants make during an interview. Does the table below represent the probability distribution? If so, create a probability histogram. So the first thing that we have to check, again, looking at those three things, is X our random variable? Is it numerical? And if you look at X this time, you'll notice that these are not numbers. So X is not a numerical random variable. So this is not a discrete. So therefore it's not a discrete probability distribution. And it says, if so, create a probability histogram. Well, we are unable to do that because our random variable is not numerical. So with the probability distribution, we have a description of a population instead of a sample. So the values of the mean, standard deviation, variance are parameters, not statistics. So the mean for our probability distribution is found by multiplying x times p of x and summing them all up. And again, we use mu, which is our parameter. Variance, which is sigma squared, the formula for that is given. Standard deviation, the formula for that is also given. Rounding rules. For my open math, it will tell you how to round, and then for me in class, I would tell you guys also how to round. The next thing that we have is the expected value. So expected value, or EX, is the mean value in the long run for many repeated samples of the probability weighted average of all the possible values. So E of X, or expected value, is equal to the mean, which is the sum of X times P of X. So the first example that we have down here says a lab orders a shipment of 100 test tubes a week, 52 weeks a year, from a supplier for experiments that the lab conducts. Prices for each weekly shipment of test tubes follows a distribution set below. So if you notice, we have prices and probability. So the probability that it's going to be $10 is 40%, $12.50 is 35%, and $15 is 25%. So does this follow a probability distribution? X is your random variable, and that is our price. So X is numerical. Our probabilities, you can check to see if those sum up to 1, and they do. And then also all those probabilities are between 0 and 1. So yes, this is a probability distribution. So it says, how much should the lab expect to budget for next year's test tube orders, assuming that the distribution does not change? So we need to go ahead and notice a few things. It's asking about expected value because it's asking about how much do they expect to budget. So our formula for the expected value is E of X is equal to the sum of X times P of X. So looking at our distribution over here, we're going to have X times P of X. So X is equal to $10, and that happens 40% of the time, plus X times P of X, $12.50, times 0.35, 35% of the time, plus $15 times 0.25%. And when you work this out, I'm around 2 decimal places since we are dealing with money. we get $12.13. So really quick though, this is written in weekly shipments. So this is $12.13 per week is what they're expecting to about spend in the long run for a long amount of time. But it's asking for how much should the lab expect to budget for next year's. So in order to figure out next year, so the budget for next year, so for next year, we're going to take our weekly, which is $12.13, and multiply by 52 weeks in a year. And we get that they should budget $630.76. So this would be our expected value. The example on the next page says the Mega Millions is a California lottery, and the probability of winning the Mega Millions jackpot is 1 out of 259 million. If you buy one ticket, which costs $1, find the expected value of winning the $104 million jackpot prize, assuming only one winner. So first off, this is a little bit same kind of thing. It's expecting how much, the expected value. However, it doesn't give us a table, and when they don't give us a table, it makes it a little bit harder. So we're going to have to create our own table. So in order to do that, I need to talk about what are the two things that are going on here. In this case, you either win or you do not win. So you're either going to win or you do not win. And you win. This problem that we're talking about was a $104 million jackpot prize. And so we're going to have an X and the probability, which we'll call P of X. And so let's talk about probabilities first. So it says the probability of winning the Mega Millions jackpot is 1 out of 259 million. So the probability of winning is going to be 1 out of 259 million. So put 6 zeros. So then what's the probability of not winning? Well, your denominator sample space would still be the same. But the probability of not winning would be the 259 million minus the one ticket for winning, which equals 258,999,999. So you have a huge chance of not winning. So now what happens if you do not win? Well, you didn't get the $104 million jackpot prize, but you did lose the dollar that you played, that you had to pay to play. So we're going to go ahead and say, and if you did not win something, if you lost something, we represent that by a negative value. And so you lost that $1. So we're going to go ahead and say negative $1. What happens if you win? Well, if you win, you won the $104, for this example, the $104 million prize. However, I know it doesn't seem like a big deal, but you did also lose that, put $sign there, you lost that $1 that you did have to pay to play the game. So we have our table set up here. And so in order to calculate our expected value is equal to the sum of n times p of x. And so we have x times p of x for winning. We're going to multiply those together. And then for not winning, we have our x times p of x. We have to multiply those together and then add this up. So we have the first one, which was not winning, which would have been the $104 million, minus the $1. So if you wanted to, you can write that as 103, and then all these 9s times the probability of winning, which was 1 out of 259 million, plus the probability of not winning times the value that you do not win. So we would have lost $1 times the probability of not winning, which was 258. A bunch of 9s. And then working this out, and since we are dealing with money again, we are going to go ahead and round 2 decimal places. So our expected value is negative 60 cents. So if we were to play this lottery over and over and over again a lot of times, we would expect in the long run for every dollar ticket that we spent to lose 60 cents of it. So it doesn't look like the best game to be playing. The next example says, in a statistical studies, individuals were asked to disclose the number of televisions in which they had in their household. In the following probability distribution, the random variable x represents the number of TVs in the household. So verify that this is a discrete probability distribution. So checking those 3 things again. The first thing that we have is that x has to be numerical, and it is. So x is a numerical random variable. The next one is checking to make sure the sum of all those probabilities is equal to 1. So checking to make sure that if you add these all up, you get 1, and you do. And then the third thing is that those probabilities need to be between 0 and 1, and they are if you check that. So all 3 of those things are met. Next thing it asks for is drawing a probability histogram. So the probability histogram is going to be your probabilities on your vertical axes and the random variable on the horizontal. So the random variable that we have is going to go from 0 through 9. So 0, and this is the number of TVs. Make sure you guys label your axes. And then the probabilities need to go on that vertical axis. So we're going to put probabilities over here. And the probabilities, if we take a second to look at that, the smallest one we have is a 0, and the largest one we have is 0.261. So I need to be able to go up to about a little bit over 0.25. So I'm going to go ahead and count by 0.5s and go up to 0.30. So 0.05. This would be 0.10, 0.15, 0.20, 0.25, and then 0.30. And again, feel free to squeeze those other numbers in there. It's kind of tight for me on here. A little difficult to read. So probability of having 0 TVs is 0. Probability of having 1 TV is 0.16. So again, do the best you can on these. And it is a histogram, and histograms are where your bars are going to be touching. So the next one is 0.26. Three TVs is 0.17. And the widths of those rectangles should be about the same. I know it's hard to do by hand. 5 TVs is 0.11. And then 8 and 9 are both extremely small. Do the best you can on those. I know it doesn't say this, but this is skewed right. Kind of reviewing a little bit there. The next one says interpret and determine the mean of the random variable x. So in order to do this, you guys can do this by hand and do x times p of x and sum those up, or we can use the calculator. So the first thing that you need to do is go to Stat, Edit, and enter in L1 and L2. L1 is going to be the number of TVs, and L2 will be the corresponding probability. Next thing we are going to do is you're going to go to Stat, Calc, one variable statistics, one var stats. L1 is where our list is, and our frequency list or our probability list in this case is going to be L2 is where I have that located. If you have an older style calculator, you are going to do one var stats L1, L2 like we did in the previous chapters. Go to calculate, select enter. And on here you will notice that we have both the mean and the standard deviation. So the mean is listed as 3.21 and your standard deviation is 1.74, rounding that 2 decimal places. So we got our mean of our random variable, so mu sub x is equal to, I'm around 2 decimal places, so 3.21. And it does say to interpret. So this would be if we survey many households, we would expect the mean number of TVs to be 3.21 TVs per household, per house. The next one says determine the standard deviation of the random variable x, which you guys also saw on your calculator, and that is going to be, again, the standard deviation. We use the parameter, and then you put little x, since we're talking about the random variable, is 1.74. Okay, for E, it says, what is the probability that a randomly selected household has 3 TVs? So this is going to be the probability of owning 3 TVs. And so we are going to go back up and look at our probability distribution that we have up here. And so 3 TVs, the probability of having 3 TVs is equal to 0.176. The next question says, what is the probability that a randomly selected household has 3 or 4 TVs? So I have boxed up here as 3 TVs or 4 TVs. Let's look at that. So with those two numbers with the word or, we're going to add those two values that we have together. So the probability of 3 TVs or 4 TVs is going to be equal to 0.176 plus 0.186. And we get 0.362. Part G says, what is the probability that a randomly selected household has no TVs? Well, if you go back up and look at your table, the probability of 0 TVs is 0. It said, would you consider this to be an impossible event? I'm going to go ahead and say no. And the reason why is we could have collected a sample from a different area where maybe people did have no TVs. So I wouldn't say it's impossible. It definitely looks like it's unusual. It's not very likely. But again, we would have to collect more data and from different areas to kind of have a better understanding of impossible. So on the next page, it says, according to the range rule of thumb, the vast majority of values should be within 2 standard deviations of the mean. So we can consider a value to be significant if it's at least 2 standard deviations away from the mean. And this is from chapter 3. So the range rule of thumb and identifying significant values. This is the same diagram that we saw before. And so since we are dealing with parameters, I'm going to go ahead and put mu in the middle. We're going to go 3 standard deviations each way. So going 1 standard deviation, that's our sigma. Going 2 standard deviations, which is where we get our cutoff. And then 3 standard deviations, which is where 99.7% of our data is going to lie. And so we have significantly low are values that are going to be mu minus 2 sigma or lower. Significantly high is going to be values that are mu plus 2 sigma or higher. And values that are not significant are going to be values that are between mu minus 2 sigma and mu plus 2 sigma. So the next example says, in the previous example, on the number of televisions in a household, determine if 2 TVs is significantly low or significantly high number of TVs. So in order to figure out if something is significantly low, so we'll put SL for significantly low, we're going to have mu minus 2 sigma. And for significantly high, which I'll put SH, that means we're going to have mu plus 2 sigma. So going back and looking at that previous example, we calculated our mean and our standard deviation. So I'm going to go ahead and use those numbers since we already have them calculated. And substituting those into my cutoff equations of mu minus 2 sigma and mu plus 2 sigma, I'm going to end up with 3.21 minus 2 times 1.74. And then 3.21 plus 2 times 1.74. Working both of these out, I'm going to round 2 decimal places, since that's what we've been doing for this problem. And I'm going to have negative 0.27 and 6.69. So what this is saying for significantly low is going to be that significantly low are going to be below negative 0.27 TVs. And then 6.69 means that this is for significantly high, is going to be above 6.69 TVs. So this question was asking about if 2 TVs is significantly low. Well, 2 TVs is in between those 2 cutoffs that we have. And since it's in between those 2 cutoffs, that means that it is not significant. So we're going to go ahead and write that down. So 2 TVs is neither significantly high or low. So it's neither. What about if I asked 7 TVs? Yes, that is considered significantly high. Another way to look at that is to look at your probabilities and see what the probability is. That was the second way that we learned in Chapter 3 of doing this. And if you were to look at the probability of owning 2 TVs, if you notice that value that we have here is rather large, it's greater than 0.05, and so therefore we could say that that is another way to look at that. Next thing on here is talking exactly about what that is. It says significantly high number of successes and significantly low number of successes. It says X successes in trials is significantly high if the probability of X or more is less than or equal to 5. Likewise, it's significantly low if the number of X or fewer is going to be less than or equal to 0.05. The next example on here, we are going to work out together